So far, I have introduced real eigenbasis theorem with the assumption that we have for an n by n real-valued matrix, and we have n independent eigenvectors. In that case, we can easily represent a general solution for the homogeneous system. I also introduced the complex eigenbasis theorem. That is, we assume we have those conjugate eigenvectors. So if you have a total of p pairs, that means you have 2p complex eigenvectors, although complex valued. And again, so we suppose we have a total of n independent complex eigenvectors, and then we can represent solutions. But we can join the two versions, and we can have a theorem for a system of homogeneous problem. So of this kind, so where this matrix A is a constant coefficient matrix with real entries. And we can allow A to have real eigenvalues and complex eigenvalues. As long as we have n independent eigenvectors. That means for this n by n matrix, if we have n independent eigenvectors, but for eigenvalues, it's okay, some eigenvalues are repeated. So as long as the assumptions that we have n independent eigenvectors, then we have this combined version that is called the real and complex eigenbasis theorem. Let's look at the assumptions. Again, A is an n by n real-valued matrix. That means each entry of the matrix is a real number. And this matrix A has some real eigenvalues. For example, we list all the real eigenvalues, lambda j. J is from 1 to q. That means we have a total of q real eigenvalues. And we have p complex eigenvalues. Actually, not p. As long as you have, for example, a complex eigenvalue, right, alpha j plus I beta j. As soon as you have this complex eigenvalue, we know its conjugate, alpha j minus I beta j, is also an eigenvalue of the matrix A. So that means if we have p distinct complex eigenvalues, alpha j plus I beta j, then we have their conjugates. So here we list all these pairs. So this is all these pairs. So p pairs, complex eigenvalues. And for each alpha j plus I beta j, suppose its corresponding eigenvector is uj, the vector uj plus I wj. Recall that u is uj is a vector, wj is the vector. They are respectively real part and imaginary part of the eigenvector corresponding to this eigenvalue. So I can put when this conjugate is an eigenvalue, then the corresponding eigenvector will be the conjugate vector, which is uj minus iwj. So anyway, so we just remember this. Suppose we have j from 1 to p. That means we have, you see, plus minus will give a pair of eigenvalue and a pair of eigenvectors. So we have p pairs. If p pairs, that means we have 2p, right? 2p total number of complex eigenvalues. So that's why this 2p. So 2p, that's the total number of complex eigenvalues, plus q is the total number of real eigenvalues. Together, we have n distinct n eigenvalues, including those repeated, because some eigenvalues may be repeated. So n, although we have, you see, together all these real eigenvectors or complex eigenvectors, and we have n independent eigenvectors. However, if we do not want to use these complex vectors to be included in the set, so we want to use the real valued vectors. So here is a set of real valued vectors. So we see that v1, v2, vq, those eigenvectors corresponding to the real eigenvalues, right? They are all listed. So a total of q real valued eigenvectors. So we remember these vectors may correspond to some repeated eigenvalues. So that doesn't matter. So we just list all these q eigenvectors. And then this pair, we can extract the uj and wj so that we can, for j is 1, that's u1, w1. For j is 2, u2, w2. And then for j is p, p, when j is p, then up, wp. So we have p pairs of real valued vectors. And they are all independent. Yeah, so this is a set of independent vectors. So this, we have an independent set, a total of n independent vectors. Yeah, a total of vectors, okay, the set of n vectors, and they form a basis for Rn. Okay, that's the assumption. And then once we have this, then we can represent a general solution. That is for the real eigenvalue and the real corresponding eigenvector, then we have an integral curve of this form. And for the complex eigenvalue and complex eigenvector, and we will be able to give solutions of this form. So then together we can get general solution of this form, depending on how many eigenvectors. So then we just see that you see this is a solution corresponding to an eigenvector, but this is a multiple of that solution, still a solution, right? And a multiple of this solution, still a solution of a homogeneous problem. So we can allow those constant coefficients to appear. So that's Kj, Hj, those Hj, Kj are the coefficients. So these coefficients will appear in this form that to guarantee no matter what they are solutions of this homogeneous system. However, we can require this solution to satisfy the initial data, because if our initial condition is that x, when t is 0, x has a value c. The value c for that vector c should be equal to this expression when t is 0. So when t is 0, all this will be gone. When t is 0, so e to the 0 power is 1, e to the 0 is 1. So then what we're left is the mj, vj, and of course the cosine at 0 is also 1, so we can take that out. So it suggests this part and this mj, vj, the summation of all these terms, and plus the summation of all those terms, and should satisfy the initial condition. So we solve the system, the C is given, all those V, U, W are found from the matrix A. So we can solve the system for the coefficients. Then we will be able to determine a particular solution for the initial value problem. So you see those coefficients, Mj, Hj, Kj, once they are found, they will be put into the integral curve, right, into the solution formula. Then we can represent the solution uniquely for the initial value problem.